All right, in this lecture we're going to conclude our notes in section 4.2 on weight and drag. We have a problem on drag. That'll be our last problem for section 4.2. And then we'll begin section 4.3, which is Newton's third law. Our problem to conclude section 4.2 is related to drag. Specifically, it's related to the circumstance, the video that we were able to watch, in which Felix Baumgartner stepped out of the space capsule that was at 39.1 kilometers above the surface of the Earth. And we're going to describe his motion as he travels towards the Earth. To begin a description of this motion, we'll start with a free body diagram demonstrating the forces acting on Felix. Our free body diagram on the left will be for immediately after he exits the capsule. On the right will be minutes after he's exited the capsule or the spacecraft. To begin our free body diagram, in our circumstance on the left, we'll of course draw a dot, and that dot represents Felix's body, or the object in our case that we have forces acting on, which is Felix. There are two forces acting on Felix as he descends from the spacecraft downwards. The first is his weight. We'll draw his weight as a product of his mass and the gravitational field that he's in. That will be straight down or towards the center of mass of the Earth. We'll label that as weight. And then he has another force that's opposing his motion as he goes downwards. That force is the force that we're studying right now, which is the force of drag. Now, immediately after he exits the capsule, this force of drag acting on Felix is very weak. It's a very weak force. It's a small magnitude. So the magnitude of the force of drag acting on Felix at this moment is small. The reason is because the velocity is small. Right? He has just exited the capsule. Not much time has passed, so he hasn't had much time to fall, to pick up speed. Because he's not moving at a very high velocity, the force of drag acting on him is also very small. We represent that he is small with a short drag vector opposing his movement downwards. That circumstances have changed on the right here. So now we have the free body diagram of Felix after some time. A good amount of time has passed. We draw a dot to represent Felix. And then we represent the forces that are acting on him. We still have the force of weight that's acting on Felix. That has the same magnitude as it had before because he has the same mass and is in the same gravitational field. If neither mass nor gravitational field has changed, then his weight has not changed. The force of drag is still opposing his descent, but now we'll say it has been long enough for that force of drag to get strong enough that it is just as strong as his force, as the weight that's acting on him, or the force of gravity. So we'd say the force of drag is just as strong or is equal to his weight. Because these are the only two forces acting on him, we could say the net force is 0. Right? These two perfectly oppose each other. If the net force is 0, by Newton's second law, we would say then that the acceleration is 0. If the acceleration is 0, we can conclude that his change in velocity is 0. So his velocity is not changing. He's at some terminal velocity. When we say terminal velocity, we mean the velocity that an object travels when the force of drag is just as strong or has the same magnitude as the object's weight. Here that circumstance was not true on the left. The force of gravity acting on him was greater than the force of drag. Because they weren't the same, then there was some net force. that net force would be based upon our diagram here, in the negative direction. Because the net force is in the negative direction, his acceleration is also in the negative direction. So he is changing his velocity, right? It's not equal to 0. There is some change in his velocity because he's accelerating. Why is he accelerating? Because there's a net force on him. Why is there a net force acting on him? Because the weight is stronger than the force due to drag soon after he leaves the capsule. After some period of time, however, eventually the force of drag increases enough because he's been traveling faster and faster and faster, right? He's been accelerating until finally he gets to a velocity that's so fast that the force of drag is just as strong as his weight. All right, that's enough analysis of the forces acting on Felix as he's descending. Now we'll look at our second question here. If the speed of sound is 343 meters per second, that's how fast sound moves. So if I shout at someone and they are 343 meters away from me, then if they can still hear me, that sound from my mouth yelling at them won't get there until a whole second later. So maybe they would see me yelling, but they wouldn't hear me yelling in a second later, if they're 343 meters away from me. Anyways, importantly for this situation, we're saying, well, this is the speed of sound. We're asked, well, how long does it take Felix to reach that velocity? How long does it take him to go from the capsule, the velocity he has in the capsule, to the speed of sound, 343 meters per second? Importantly, we're going to neglect drag in this circumstance. That is a reasonable assumption. It's a reasonable assumption because his movement through space for the first minute or two looks a lot more like this on the left than this free body diagram on the right. The reason for that is because not only is his velocity starting relatively small, but eventually it does become large, right? This is no small velocity, but the density of the air in the atmosphere that high up is also very small. Not only is his velocity small to start with, of course maybe that velocity increases, it does increase, there is some change in velocity, but the density at 39.1 kilometers above the surface of the Earth, the density of air is very small. So it's reasonable to make some calculation of how long it takes him to reach this velocity by neglecting drag. That's a reasonable assumption. All right, now we need to assess, well, what kind of problem and what are we trying to solve here? What are we trying to understand about Felix? Well, we're given some velocity he needs to get to. We're trying to see, well, how long does it take him to reach that velocity? What we should be thinking is, this is something where I'm asked to describe the motion of an object, in this case Felix, so we should be thinking I have the tools of kinematics to help me figure out what is happening to his velocity, or importantly, how long does it take him to reach that velocity. Remember, our problem-solving techniques for kinematics is to start with a T-chart of knowns and unknowns, so that's what we'll draw. Draw a T-chart of what do we know about Felix's motion, what do we not know. We know that he's going to reach a velocity of 343 meters per second. That's his final velocity. He'll eventually get to that velocity. He starts at a velocity, though, of what? What is his initial or starting velocity when he exits the capsule? Well, if he's just walking off the edge of the capsule, then it's just 0. It's 0 meters per second. In what direction? We'll say the positive direction is down. That makes everything easy for us. We'll say that down is positive. We'll also draw a bit of a picture here if we like to make some sense of what's happening here. Here's a balloon attached to the capsule. That's what we saw. Here's the door to the capsule. And then we can draw Felix down below, falling down. There is Felix falling. as he exits the capsule, he's heading down. He starts with a velocity of 0 meters per second because he just walks off the platform. After some period of time that we don't know, that's one of our unknowns, we don't know how long it takes for him to eventually reach this velocity. We do, however, know that because we're neglecting drag, based upon our free body diagram, what is the only other force that's acting on Felix? That would be his weight, or gravity. If the only force acting on an object is gravity, what must be his acceleration? It must be free fall acceleration, which is 9.80 meters per second squared, because it's accelerating or his velocity is changing in the positive direction, then that acceleration is positive. We're also asked to find how far he travels in reaching the speed of sound when he finally gets to this velocity. So that's another unknown for us. That'd be change in x, or the displacement. Our first task is to find how long it takes him to reach that velocity. We need a kinematics tool, an equation that relates these three knowns to this one unknown. We have our first kinematics equation to accomplish that. We know our final velocity, we know our initial velocity, we know the acceleration. We just need to find time, our one unknown in this equation. To get time by himself, first I need to subtract initial velocity. So now I have final velocity minus initial velocity equals acceleration times time. Now I can divide by acceleration. So my final equation is, since acceleration on the right-hand side cancels, is that my change in time equals final minus initial velocity over or divided by the acceleration. If I plug the values that I know in, 343 meters per second minus 0 meters per second, divided by 9.80 meters per second squared, I find that the time to three significant figures is 35.0 seconds. So we found time, the amount of time that it takes for him to reach the speed of sound, 35 seconds. After 35 seconds of falling, he is at the speed of sound. Now we need to see, well, how far has he traveled in reaching the speed of sound? So we need a way to relate change in position to any of our four variables that we know now, because now we know the amount of time in which that happened. Our second kinematics equation will come in handy here. Our second kinematics equation is useful because we know the initial velocity, that's 0. We know the amount of time that it happened, or that in which he reached final velocity of 343 meters per second. That would be in 35 seconds. We know his acceleration, and again, we know the time. This whole term here falls away because our initial velocity is 0. 0 times time is 0. So I can cross this out. Now I just need to input what I know about his acceleration, which is free fall acceleration. Input the time in which he falls to reach 343 meters per second. So we have 1/2 times our acceleration of positive 9.80 meters per second squared. I know his time, that is 35.0 seconds squared. That equals 6,002 meters. I have three significant figures here that I can work with. I can't just write 6,000 because 6,000 has only one significant figure in it, 6,000 meters. So I have to use scientific notation. 6.00 times 10 to the third meters. That would be his displacement, specifically in the positive direction. That would be how far he traveled in a period of 35 seconds. Over that period of time, he reached the speed of sound, 343 meters per second. Now, next we're asked, we're going to ultimately find what is the force of drag, that should say drag, that's acting on him. We'll first, however, look at his weight. How do we find Felix's weight? Well, what do we mean when we say weight? Well, we mean that it's the force of gravity acting on an object. I can find how strong that force is if I know the mass of the object and the gravitational field that the object's in. We know from our problem that the mass of Felix, he's been weighed at 110 kilograms. 110 kilograms is his mass. His gravitational field is that of Earth, 9.80 newtons for every 1 kilogram of mass. So we find to 3 significant figures that his weight is 1,080 newtons. If you put it in your calculator, you may get something like 1,078. That measurement has 4 significant figures. That's too precise. We need a measurement that has a degree of precision with 3 significant figures because this is a product. We're multiplying 2 things together. This measurement has 3 significant figures because of that decimal point there. This measurement also has 3 significant figures. So our weight in newtons can have 3 significant figures, 1, 2, and 3. Our last question for section 4.2 is if he reaches a terminal velocity of 110 meters per second, what must be the force of drag that's acting on him? Our key term here is that he's at terminal velocity, and we're trying to find drag. Well, what do we know about the forces acting on an object that are at terminal velocity? That's what we saw up here. We know that the force of drag at terminal velocity is equal to the weight of the object, or that just as much as gravity is pulling on the object, the drag opposing that object's motion is the same magnitude, or opposing it just as strongly. We just found his weight, and by terminal velocity we mean that weight is equivalent to drag. So we know that the force of drag acting on him must have a strength of 1,080 newtons, but in the opposite direction. We'll say one final word to overview everything we've done so far, to finish up section 4.2 for today. We have that Felix Baumgartner, that has a mass of 110 kilograms, fell from 39.1 kilometers above the surface of the Earth. Our free body diagram on the left here demonstrates that soon after he left the space capsule, though he had a force of gravity acting on him, the force of drag acting on him opposing his motion was very small because his velocity was small. It's also small because the density of air, 39.1 kilometers above the Earth, is very small. Both of these values affect how strong drag is. Because the weight is greater than the drag, there's an imbalance of forces, so there's no equilibrium. So the net force is some non-zero number. In this case, because the weight is stronger than the drag, that's in the negative direction, so we have a negative net force. That means our acceleration is in the negative direction, so we have some change in velocity. It's not zero. His velocity is changing. Eventually, he reaches at such a high velocity that the force of drag is now strong enough to directly oppose weight. Because that's true, then now there is a balance of forces. The net force is 0, so his acceleration is 0, so he's no longer changing velocity. So he's reached terminal velocity. Here we found that if we neglect drag, we could find that after falling for 35 seconds, he reached a final velocity of 343 meters per second, or the speed of sound. In reaching the speed of sound, he traveled a distance of 6,000 meters. or 6.00 times 10 to the 3 meters, or we could say 6 kilometers. His weight depends on his mass and the gravitational field he's in. His mass was 110 kilograms, gravitational field 9.80 newtons per kilogram. So the force of his weight of gravity on him is 1,080 newtons. That is the same force, if he's at terminal velocity, that is the same force that drag is imposing on him, causing him to stay at a constant terminal velocity. Thank you.